All right, last time we went over measures of center of data. This time we're going to be looking at measures of variation. That's how spread out your data values are. So starting with the definition, the range of a set of data values is the difference between the maximum data value and the minimum data value. Range is just one of the measures of variation that we can use. And we have a round-off rule for measures of variation. It says when rounding the value of the measure of variation, carry one more decimal place than is present in the original set of data. Wasn't that the same round-off rule we use for measures of center? Yeah, I thought so. Next definition is that of a standard deviation. And the standard deviation is kind of difficult to understand. It's a numerical value, measures how spread out the data are. The smaller the standard deviation, the less variation there is in your data. The larger the standard deviation, the more variation there is in your data. S is the variable we use to denote the standard deviation. I'm going to kind of take you through how this is kind of developed. What it does is it measures the difference between the mean and your data value. The mean is a measure of center. So if you've got a list of data here, let me just kind of do a plot here, and we have a mean value here. Let's say that this is the average value, X bar right here. And you've got a bunch of data points. Some are above, some are below, but the middle of the data has to go through, where the middle of the dots are here. What we do is we measure the difference between this data point and the average, and that's going to be X minus X bar. Remember, X bar is the measure of center. This is called a deviation. If your data value is above average, you're going to have a positive deviation. If your data value is below average, you'll have a negative deviation. So this point right here that I just plotted and drew the blue line to the average value, that's below average, right? It's less than average. So this would be a negative number here. So we would have a negative value here. And if I go to the next point and I measure the deviation, that X minus X bar would actually be a positive value, wouldn't it? So we would be looking at all of these measures of deviation. Some are above average, some are below average. But when I add all these deviations up, guess what I have to get? The sum of these deviations, the data values, the data minus the average, has to be equal to 0. Because if the X bar is truly the middle value, then you're going to have the same amount above average as you have below average. Well, we're trying to get an average deviation. That's what we call the standard deviation. So we need a way to come up with a measure, and if we just add up all the deviations, we get 0. That's not helpful. So somebody said, well, okay, let's square this. Then the numbers are always positive, right? So what we did then is we said, okay, we'll square these deviations, and that's going to be a positive value. And we'll add them all up and divide by how many there are, -1. Now the -1 is going to be kind of trippy. This part right here should be okay. This part right here is how we come up with an average, right? You add up everything you have and divide by how many you have. That's what we do with the deviations to come up with an average deviation, but we have to say -1 because of something called degrees of freedom. And that's a more complicated concept. For now, in an intro course, I would say accept what I say, but if you want to know why, I can explain why after class. I just don't want to take class time out to do it. Now, remember, we squared these deviations. And in order for this to be a valid number, let's say my data values were dollars that I was talking about, an income or something, and I wanted to know what the standard deviation is for the income. Once I square these data values, we're talking now the units are square dollars. Square dollars don't make sense, do they? So in order to undo the effect of the square, we have to come along and take a square root. Now the units will be back in dollars again. And this happens to be the formula for the standard deviation, as you can see in your notes right here. This is the sum of the square of the deviations divided by the number of deviations minus 1, and then we take the square root. I guess I should have used the sample statistic S as opposed to the population parameter sigma. The way that you would read this, or the way that I hope you would think about this, is it's the sum of the squares deviations divided by the number of data minus 1, and then we take the square root. What you really need to be aware of is the larger the standard deviation, the more variation. Smaller standard deviations mean you have less variation. But here's a graphic that represents the wait time that you can expect to have at 3 different banks. In the first bank, you know how the tellers are lined up in a row? The manager is OCD and strictly controls the wait time of people. Like he stays on top of the tellers to make sure that they don't spend too much time with the customer and everything. Okay, the average wait time at the first bank, because the manager is strictly controlling the tellers and everything, staying on top of things. We have 3 customers come in. The first customer's average wait time is 4 minutes. The second customer's average wait time is 4 minutes, or wait time, not average wait time. The first customer waits 4 minutes in line. The second customer waits 4 minutes in line. The third customer waits 4 minutes in line. And here we would say that the average wait time is 4 minutes, and the standard deviation is 0 because every customer waited the same amount of time in this first bank. The second bank, no, is kind of like, it still has the turnstiles like they do at amusement parks, where you go through and you go to the next available teller. Well, the first teller is pretty quick, and she gets the customer out of there in 2 minutes. The second customer has to wait a little longer. They got to wait 4 minutes, and the third customer has to wait even longer still. They had to wait 6 minutes. The average here is still going to be a 4-minute wait time. But the standard deviation is now, it's greater than 0. It's a positive value. In order to see what the standard deviation is, let's just plug those numbers in. We're going to go to Stat, Edit, List. We have 2, 4, and 6. And then we quit, go to Stat, and then we're going to calculate our 1 variable statistics for list 1. And we see that the standard deviation is 2 here. The third bank is like it is at the supermarket, where you have to wait. You pick your line and then you wait. So if I go to checker 2, I could get out quickly if that checker is efficient, or I could be stuck in line and watch 3 people on the line next to me go through the checker. Or the first teller gets the person out in 1 minute. They're good. The second teller gets the person out in 2 minutes. They're good as well. The third teller has to wait. Person is unlucky. They go and they have to wait all this time. Let's see, how many minutes does it have to be in order for the average to be 4? So we'd be up here at 9 minutes. So now the average here would be 4. All these banks have the same average. But when we look at the standard deviation, let's go to Stat, Edit. We'll go to List 2 and we put in 1, 2, and 9. Stat, 1 variable statistics. We want to do List 2, and we see that the standard deviation is now 4.35. So we've more than doubled it, 4.4. So we'll call this standard deviation 4.4. So the larger the standard deviation, the greater the variation is amongst the data. If all the data values are the same and you have a uniform distribution like we do here, then there's no variation in your data. The standard deviation would be 0. Because we're squaring square roots, the standard deviation is also never going to be negative. So does this kind of give you a better feel for what that number means? It's how spread out the data values are. Some important properties. The standard deviation is a measure of variation of all values from the mean. So we're looking at how far apart the data values are from the average. And that's what I was trying to show you with this picture here. We're looking at how spread apart things are from the mean. The value of the standard deviation is usually positive. It's never negative. It could be 0. That's why we say it's usually positive, because 0 is neither positive nor negative. And then the value of the standard deviation can increase dramatically with the inclusion of 1 or more outliers. You see how this outlier right here made the standard deviation jump really high, well, those outliers will really have a dramatic effect on the standard deviation. Also, the units of the standard deviation are going to be the same as the units of the original data values. Because we squared and then we took the square root, our units are going to have the same values. So here's an example problem, or use either formula. There's two formulas there, but what I'm going to urge you guys to do is don't memorize formulas. Use your calculator and do the one variable statistics like I just showed you with those examples. So we're going to pull up our calculator. If these are the numbers of chocolate chips inside of the chocolate chip cookies, we can put this in our calculator, and you need to practice doing this. We're going to be using the one variable statistics here. So we're going to edit, and I can clear out what I have in list 1 by highlighting the name of the list, hit clear, and then enter, and we type in our values. There's 22, 22. This author's really fond of chocolate chip cookies. Have you noticed that? Once you get your data into the calculator, what's the next step? Get out of the program. Second, quit. Now what? Go back to stat. Go over to calculate, one variable statistics. And since I use list 1, I can just hit enter and it'll give me list 1 as the default setting. The average number of chips inside the chocolate chip cookies is 23.5. The standard deviation now is 1.9. We go out to 1 decimal place more than our original data. Since we were using whole numbers here to measure the chips, we can go out to 1 decimal place. So there's your mean, and this number right here, the SX, is the sample standard deviation. This number right here with the sigma on it is the population standard deviation, and we don't know the population standard deviation. Your calculator uses a different formula to calculate this number. They'll be really close but not the same. For the purposes of this class, always use the sample standard deviation. That's the one with the S on it, this one right here. The range rule of thumb for understanding standard deviations is based on the principle that for many data sets, the majority, or 95% of the sample values, lie within 2 standard deviations of the mean. 95% is kind of our cutoff for usual versus unusual. That other 5% we consider to be unusual. So if we're within 2 standard deviations of the mean, then we're considering these to be usual values. So the range rule of thumb is what we use to measure our minimum usual value. We take the mean and we subtract 2 standard deviations. To get the maximum, we take the mean and we add 2 standard deviations. And I think a picture is worth 1,000 words, so I'm going to draw a picture of what's going on here. If your data are normally distributed, and we're operating under the assumption that they are normally distributed, what does normal mean again? Symmetric and bell-shaped. So if your data are symmetric and bell-shaped, then your mean is going to be right here in the middle. And if we go out 2 standard deviations, whatever that standard deviation is, there's 1 standard deviation, 2 standard deviations. This number right here is going to be the mean minus 2 standard deviations. When we go out 2 standard deviations to the other side, this number right here would be the mean plus 2 standard deviations. And in between here is our middle 95% of the data. So everywhere between here is 95% of the data. So this number right here and this number right here would be the cutoff points for what we consider to be usual versus unusual. For example, if we're looking at IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. If you want to know what the cutoff is for unusually high or unusually low IQ scores, we would take the mean and we would subtract how much for unusually low. 100 minus 30 is 70, so 70 separates the unusually low from just the low IQ. And if we add 2 times 15, we end up with 130. So any IQ score between 70 and 130 would be considered usual, normal. So what that means is, or the implication is, IQ scores between 70 and 130 are considered usual. We wouldn't consider them unusual. The range rule of thumb for estimating a value of the standard deviation, if you don't have your calculator and you're able to put the data into a list and do all that good stuff, and you want to estimate what the standard deviation is, you take the range of the data. Remember how we calculated the range? We did the maximum value minus the minimum value, and then we divide that by 4. And the reason we divide by 4 is because we have 2 standard deviations to the left and 2 standard deviations to the right. If 95% of our data fall within there, we could say divide that by 4 because these have to be equally spaced. The standard deviation's the same there. So that distance between one standard deviation to the left and one standard deviation to the right, this number right in here is going to be a standard deviation, and there's 4 of them. That's what we call the range rule of thumb. All right, using 40 chocolate chip count for the Chips Ahoy cookies, the mean is 24 chips. The standard deviation is 2.6 chips. Use the range rule of thumb to find the minimum and maximum usual numbers of the chips. Would a cookie with 30 chocolate chips be unusual? Well, here's the mean, 24. In order to find out our minimum value for the unusual, the low end, unusually low, we would take the mean minus 2 standard deviations. For this problem, that would be 24 minus 2 times 2.6. Somebody got a number for that? How many? 18.8? So any cookie that has less than 18.8 or less than 18 chips, less than 19 chips in it would have an unusually low number of chips. What about unusually high? What would we do? This is a S, not a 5. That's a standard deviation. Okay, handwriting's getting me. So the mean here is 24, and then that's 2 times the standard deviation is 2.6. So that's 24 plus 5.2. And that would be 29.2. So would a cookie with 30 chocolate chips be considered unusual? It's more than 29.2. 29.2 is the hard and fast cutoff. You can't look at this and say, well, 30 is close to 29. I'll let it slide. No, you can't do that. In the world of statistics, there has to be a point at which things go from usual to unusual. This number right here is that point. This number is above that point, so 30 would be considered unusually high. You can't say, oh, well, it's close enough, I'll let it slide. Nuh-uh, it's unusually high. Variance. Variance, the units on variance don't really make sense because what variance is it's the square of the standard deviation. Remember we said in order to find the standard deviation we had to square whatever the units were. And then we took the square root and that gave us the standard deviation. So the units here for the standard deviation are the same as they are for whatever your data measure. But here they're units squared. It doesn't make a whole lot of sense, but the variance comes in handy in the future when we start working and manipulating formulas. So that's why it's a value that we're going to talk about. We're not going to talk a whole lot here, but this is what you need to keep in mind. The variance is the square of the standard deviation. If you see an S, you know you're looking at a sample. If you see a sigma, you're looking at a population. Very good. All right, unbiased estimators. The sample variance, S square, is an unbiased estimator of the population variance, which means that the values of S squared tend to target the value of sigma squared instead of systematically tending to either overestimate or underestimate the value of the sigma squared, the population variance. Unbiased estimators are what we aim for when we start doing inferences or making conjectures about populations. The mean is an unbiased estimator, the variance is an unbiased estimator, and those are good things. Okay, that's what we strive for. Remember when we talked about self-selected survey, that's not a good survey method because it can introduce what's called bias. Bias is what you have whenever you favor the outcome one direction or the other, either an overestimate or an underestimate. Now, this is the rule that I've been dying to get to because it's a much prettier picture than what I can draw with a normal graph. This is the empirical rule, or it's sometimes called the 68, 95, 99.7 rule, for a very good reason. If this X right here is the middle of your data, X bar, that's the mean, measures the center of your data. If we go out one standard deviation to the left and one standard deviation to the right, we find that 68% of our data lie within one standard deviation of the mean. If your data come from a normal distribution, it does not matter what the mean or the standard deviation is, this relationship will always hold true. We could be talking about weights of people. We could be talking about pulse rates. We could be talking about height. And whatever the mean and the standard deviation are, 68% of the population will lie within that one standard deviation of the mean. That's kind of cool, and it comes in handy for writing programs and finding probabilities, as you're going to see later. I'm getting excited about it. Can you tell? Go out 2 standard deviations, and we have 95% of the data that lies within 2 standard deviations of the mean. And remember, that's where we cut off our usual from our unusual, because 95% is a lot, but it's not so much that we have to be crazy about it, right? And then if you go out 3 standard deviations, 99.7% of the data lie within 3 standard deviations of the mean. Because of this, we can then calculate the value or the percentage of a population within each one of these individual columns. These happen to be the exact values, and they've used a formula in order to calculate this. This happens to be 68.26, but we said about 68%. It just has to be close enough for government work. This table is something that I would print out and keep handy as you're doing homework. It's got a lot of information in it, but do you see now why it's called the 68, 95, 99.7 rule? 68, 95, 99.7 rule. It's a good rule. Learn it, love it, live it. This wraps up section 3.3, and we will move on to section 3.4.